Welcome to solverfy.
We're asked to prove that Sollin's algorithm produces a minimum spanning tree in a connected undirected weighted graph. So we're essentially proving that Sollin's algorithm does what it says it does. So to do this, first, let G be a connected undirected weighted graph. And now, let S be the tree that's produced by Sollin's algorithm. Let E1 through En minus 1 be its edges in the order chosen. And we have the edges that were chosen in the same stage. We really don't care about how these are ordered. It's just arbitrary. What matters is that edges that were in one stage come before edges in a stage that came later. And now, let T be a minimum spanning tree that contains all the edges, E1 through EK. Where K lies between 0 and N minus 1. Now let's assume that K is less than N minus 1, and we'll derive a contradiction. Now let S prime be the forest resulting from Sollin's algorithm for S. At the stage before the edge EK plus 1 is added. And now, let's C be the component in S prime that results from the addition of EK plus 1. And now let ek plus 1 be labeled u, v as an edge. With u, of course, is going to lie in the component c. I guess I should say instead of resulting from, this is responsible for. And we have that v, of course, is not going to lie in c by Sollin's algorithm. Now, let P be the unique path from U to V in T. And this exists because T is a tree. Let E prime be the first edge in the path P that is not in S prime. And we know that this E prime exists because the two vertices are in different trees in S prime. And so this implies that E prime is incident to C. And we know that the algorithm added ek plus 1 on behalf of C, so it follows that the weight of ek plus 1 has to be smaller than the weight of E prime. Or if they're equal weight, ek plus 1 comes first in the lexicographic order. You can also write this as W of ek plus 1 is less than or equal to W of E prime. Now, we also know that E prime will be added on behalf of the component containing vertex V. Now, if E prime does not lie in E1 through EK, so we'll suppose this. So E prime is not one of those edges. We can continue on the path P until we obtain an edge not in E1 through EK. And the reason that we know that ER exists is because If it doesn't exist, we'll be creating a circuit. And we know from the previous exercise this is not possible, that in each stage of Sollin's algorithm we create a forest. And so that we have that, therefore, the weight of EK plus 1 is going to be less than or equal to the weight of ER. And now, let T prime be the tree which results from taking the tree T and adding the edge EK plus 1 and subtracting the edge ER. Then we have clearly that the weight of T prime is less than or equal to the weight of T. And so T prime contains edges E1 through EK plus 1. And it follows T prime is a minimum spanning tree. But this is a contradiction because we assumed that k was the largest integer such that tree T was a minimum spanning tree. So we assumed that k was the largest possible value for which E1 through EK was a minimum spanning tree. And we have now obtained that E1 through EK plus 1 also forms a minimum spanning tree. Therefore, k is equal to n minus 1, and so it follows that s equals t. And therefore, S is a minimum spanning tree, as the algorithm claims.